All right, guys, glad you could join me today. You can see today's lesson is on what we call calorimetry. So that term should look a little, at least the first part of it should look familiar to you. Calorie, you guys remember that's an energy unit. And metry is the study of or the measurement of. And so we're going to measure calories. So for example, right, I have this apple. And you guys know what food is. You guys know all matter contains energy. There's energy stored in matter via the bonds between the atoms. And all food is a certain type of matter that we can utilize, we as people can utilize to extract the energy from that food item and then utilize it for our daily functions. So I don't know about you, but I was always wondering how do we know how many calories, for example, a food item has? For example, this apple might have 100 calories or something, I'm guessing. You know, have you ever wondered that, right? When you guys go to the fast food, now they have to display on the menu board how many calories is like in a Big Mac or whatever. You probably wonder how would they determine that? Well, let me show you how they would determine that. That is via a calorimeter. So here is a calorimeter. I got to show you guys the inside. I'm going to actually show you a schematic that will give you guys a better idea of what's going on. So, you guys look, so this would be a calorimeter. So basically what they would do is, in a calorimeter, they take the food item, i.e. the apple here, for example, put it in here. I don't know if you guys can see there's like an ignition source, and what they would do is essentially blow up the food item. Because when you blow up the food item, basically what you're doing is you're breaking bonds, and you're decomposing that item to its most simplest forms, ideally even to the elemental form. Well, you imagine when you blow it up, what's going to happen is heat energy is going to be released. So the energy that's stored in the bonds within this apple, as bonds break and new bonds form, energy is released. Well, the energy that's released in the full decomposition of that food item is what we would say is the energy content of that food item, which we describe in calories. So we have that apple, we blow it up. You guys can imagine heat is going to be released. So what we have in a calorimeter is we actually have an outside container, and the food item is actually placed in an inner container. And I don't know if you guys can see from this, but it's kind of bluish here, indicating that there's water in between the two containers. And that's exactly what we would see in this. See, here's kind of the ignition source here. And we'd have, you know, a container within a container. And between those containers would be water, okay? So you can imagine if heat is released from the food item, we can't really measure directly how much heat that food item gives off, but we can measure it indirectly. You think about it, heat's given off. What's going to absorb that heat? Isn't the calorimeter itself going to absorb all of the heat that was given off from the combustion of that food item? So you can imagine, we're going to make this really simple now. The calorimeter does consist of a metal construction, but we're going to just go, for simplicity's sake, we're just going to say just the water itself absorbs the heat that was given off. So we will then, so what we'll say here is, we're going to make a statement. We're going to say that the heat loss, oh, you probably can't even see that because I think I have the camera down. The heat loss by the food item, we would say theoretically is going to be equal to the heat gain by the water. So that's the statement we're making. Let me look on the video and make sure you guys can see that. Yeah, okay, you guys can see it. So the heat lost by the food item when we combusted it, we blew it up, right? So theoretically, all that heat would be gained by the water, and therefore, if we can figure out how much heat the water gained, we could ultimately figure out how much heat the food item gave off, and thus how much energy did that food item contain. So you guys, we're going to kind of demonstrate that, and that's why I have the camera a little lower. For example, I have a pecan here. Let's say it weighs about 10 grams. The pecan. Well, the pecan has amount of energy, so what we're going to do is have a little simple setup here. It's going to be very simple to show you how we could ultimately calculate how much energy and thus how many calories this food item has. So what I'm going to do is I'm going to take that pecan, I'm going to put it on I just kind of skewered it on a safety pin here, on a pin here, and then I'm going to place it, and you guys can imagine I'm going to place it under. You guys see this is called the flask. And you guys could probably imagine, based on what we just described a calorimeter, I'm not doing it in a full calorimeter, what do you guys think I'm going to put in the flask? You guys remember what we were talking about with that calorimeter? There was water. So what I'm going to do is I'm going to place water, and so I want to have a certain amount of water. It doesn't necessarily matter how much, but what I want to do is I want to record how much water I'm putting in there. So the glassware of choice is going to be a graduated center. That's what we use to measure the volume of a liquid. I'm going to place that on a flat surface. I'm going to read, and I already poured it ahead of time just to make for easier numbers. Let me turn this off. And so I have 40 grams. So basically what I'm seeing here is we're going to ultimately be able to use the specific heat formula. This is what we had initially taught you there in the last video lesson. So what that tells us is I can figure out how much heat is gained or lost by a substance if I know the specific heat of the substance, I know the mass of the substance, and I know how much temperature, the temperature change of that substance. So you guys, we're going to do this with water. So I'm going to, I have some water. I have 40 grams of water. So I'm going to write that down here. Or I'm sorry, basically, I'm kind of jumping the gun. I have 40 milliliters of water, okay? Because that was milliliters, so I'm going to put that in here. And you guys, I'm going to get this going. So ultimately, I think you guys can kind of see how the setup is. Basically, the nice thing about a pecan is, with all the oils in the nut, I can actually just light that straight. And actually, I need an ignition source. And you guys can see why I placed the water over that, because you guys know heat rises. So I'm going to get this going. But before I do this, some of you guys might already be on top of this. Before I light this up, there's actually one other piece of data I need to collect. Notice I got how much water I'm using. But there's another piece of data I need to collect before I light that up. Some of you guys might pick that up. What I need to know is, if you guys look in the formula, oh, I might need to know what is the initial temperature of that water. So I'm looking, initial temperature of that water. In fact, I'm going to write that down. The initial, I'm going to put TI, that's the initial temperature. It is 20.3 degrees Celsius, okay? So I'm going to write that down. So I've done that. And so at this point, now I'm going to light this up. You guys can see that's what makes this a little easier to work with. You notice that pecan, it's flammable, right? Those peanut oils are flammable. You guys notice I couldn't do that with this apple. The apple's not flammable. You guys would know that because most fruit and vegetables are primarily water. That's why I would need specifically a bomb calorimeter. So I would have to have an ignition source to blow this up as opposed to just lighting it like that. So obviously you guys can see, you guys see that pecan burning, and you guys see all that, you think about all that energy of that heat and the light that's coming from that. You guys, where is that coming from? That's coming from the pecan. Remember, all that energy was stored in the pecan. And what we're doing in the reaction, and you guys remember whenever we burn something, what's it usually reacting with? Oxygen. We're releasing, some of those bonds are breaking, new bonds are forming. You can see some ash and some smoke's given off. But you can see a lot of heat energy, which might not be surprising as you guys would think with a pecan. You're thinking, you know what, that's probably pretty high in calories. So it's not surprising that we notice, you can visibly see a lot of energy given off in the burning of that pecan. And as you guys could see, you guys could probably guess, you know, if I'm looking, what do you guys think I'm noticing right now as I'm looking at the thermometer? What do you guys think I'm seeing? Yeah, as you would imagine, aren't I seeing a temperature rise? Because look, as the energy, the heat energy is given off from the food item, what's absorbing that heat energy? The water. And what's the result as it absorbs that heat energy? Molecules move faster. You guys remember, that's what temperature is. It's a measure of the average kinetic energy. So as it's absorbing more, the water's absorbing more and more heat, the water molecules are moving faster and faster, and that's indicated by a rise in the temperature. So indeed, I'm seeing the temperature rise. And so you guys would probably guess, at what point would I record my last temperature? Wouldn't you guys agree? Wouldn't you just wait until the pecan is done combusting, and then I would record that as the final temperature? So I'm kind of waiting on that, just kind of waiting for that to go, just so we don't have an awkward silence. You guys, just to kind of point back to this to see where we're going. So what I want to know is, how much heat did the water gain? Because if I get how much heat the water gained, can I say, you know, I can make an assumption that that's equivalent to the heat lost by the food, which is equivalent to the calorie content of that food item. So what I'm going to solve for is Q. You guys remember Q is the heat. What I need is the specific heat. Well, what do I need the specific heat of? Well, what I'm doing is I'm recording how much heat the water gains, so I need the specific heat of water. You guys, that's the nice thing about water. We already know this specific heat of water. You guys remember, it's really easy to remember. It's 1 calorie per gram degree Celsius. That's the one I'm going to ask you guys to, okay, that's still going, to memorize. It's 1 calorie per gram degree Celsius. I need to multiply that by the mass of the water. How much water do I have? Okay, you know what? Stop right here, so let's see what we got. Okay, I'm going to record it. It's 94.3. Okay? So I need to know the mass of the water. How much water did I have here? Because wouldn't you guys agree that's going to ultimately affect, that's going to ultimately affect the temperature, is how much water you have. You guys would imagine, if I started with more water, wouldn't you guys expect the temperature to go up less? And if I had less water, you expect the temperature to go up more. So it doesn't necessarily matter how much water I have, as long as I record specifically how much water I have. But you guys will look. You guys, if you look at your units, I have a gram unit here. You guys remember, gram unit is a mass unit. Here, all I had was a volume unit. But you guys, this is the nice thing about water again. You guys, the density of water, if you guys remember from before, it's 1 gram per milliliter. That means if I have 1 little milliliter, if you guys remember 2 months ago I had a little square that's a milliliter. If I have 1 milliliter of water, it weighs 1 gram. When they developed the metric system, they did that based on the density of water. So if I have 40 milliliters of water, how much water do I have? 40 grams. And then I have to multiply that by the temperature change of the water. Well, it started at 20.3 and it went to 94.3. What was the temperature change? I just subtract that. And those of you guys who are good at math, you can see that's 74.0 degrees Celsius. Now you guys look at the units. Gram on top, gram on bottom cancels. Degree on Celsius on top, degree Celsius on the bottom cancels. And what unit am I left with? Calories, which is what I wanted. I wanted calorie. So go 1 times 40 times 74. Okay. 1 times 40 times 74. And I get 2,960. And you guys look at the unit, 2,960 calories. So you guys, this was kind of like similar to the pecan, about the size of the pecan that we had. So somebody would be looking at that and they're like, Mr. Wilson, are you kidding me? You're telling me that one pecan, that nut right there, has 2,960 calories? Are you kidding me? Some of you guys might know, right? You have a daily caloric intake that you guys should be taking to maintain body weight. And it depends if you're like a little petite girl or you're a big buff dude. But they generally say maybe on average, women probably want to consume between 1,500 and 2,000 calories a day, right? Because they tend to be smaller. And then gentlemen tend to need to consume about between 2,000 and 2,500 calories a day. And then we look at this. You're telling me, Mr. Wilson, if I eat this one pecan, I've eaten more calories in one day than I should be eating in a day based on my size? Anyone think? Anyone think, as if you guys are going to respond. But I want you guys to think, what is the dilemma here? What's going on here? Some of you guys might remember from our last video lesson, you remember these are small c calories. Remember, those aren't the same thing as food calories. Remember, 1 food calorie is what we call a big C calorie. That's equivalent to 1,000 small c calories. Because the calorie unit is so small when we're dealing with food items, that's why we kind of changed that up and made each food calorie equal to 1,000. So you guys, if I want to see how many food calories that is, what do I need to do? Divide by 1,000. 3 zeros in 1,000 makes it really easy. I just moved the decimal 3 places. You know, essentially it's like 2.96. You know what essentially that is? 3 calories. 3 calories. So, you guys think about 3 calories. Is anyone thinking about that? Thinking 3 calories. Doesn't 3 calories seem kind of small? Because you guys probably would know, like anyone who's ever thought about dieting or whatever, you guys got to be careful about that. But you guys know nuts, like pecans in particular, are not on a diet, right? It's not something you would usually want to eat a lot of if you're trying to lose weight. Why? Because they're probably high in calories. And you know how we would know that? You guys remember, you guys saw the fire, the flame, the light, the heat and the light there, a lot of energy. You're thinking that's only 3 calories. And you guys think about it, you guys really, what causes it to burn is the oils. And you guys should know oil is primarily fat. And fat has actually high calorie content. That's why they would tell you to kind of go low on fatty foods if you're trying to watch your weight. So that kind of seems low. But so I want you guys to be thinking, why would that be so low? Really, if you guys think about it, really the reason is because of our crude setup here. If you guys think about it, we made a very bold assumption that all of the heat that was lost by the food is going to be equal to the heat gained by the water. Is that necessarily the case? You think about it, we did put the water above and we could see it absorbed a lot of that heat, but you guys could probably figure out, you know, if you stood pretty close to this, what do you guys think you would experience? You would probably feel the heat. So in this kind of simple apparatus, not all of the heat was necessarily going to the water, so a very simple setup. And you guys can see how this is different than a calorimeter. Notice how a calorimeter is? It would totally enclose it, so it's going to minimize heat loss to the surroundings. So the result of this, the problem with this very simplistic setup, is that a lot of heat was lost to the surroundings. So you guys, that's part of science too. You would think, okay, knowing that, how could I modify the experiment next time to get more accurate results? When you guys agree, maybe I could lower the water so it's even in closer proximity to the burning food item. Wouldn't you also maybe do something like this? Maybe try to enclose it. Maybe try to have something that would minimize heat loss to the surroundings, so I could put, you know, I could put it in, you know, something, well, I'd have to raise it up, but I would enclose it so it's more like a calorimeter. Ideally, we would perform that experiment in a calorimeter to minimize heat loss, okay? So nonetheless, that, based on a crude experiment, that's what we've got. Lastly, so what I say, so we already talked about that, but let's say we did it really well and we still got 3 calories. You know, we kind of controlled a lot of the variables. Could I say then pretty definitively pecans are 3 calories? No, what was 3 calories? That pecan. You guys see that? You can't just make a declarative statement that pecans are 3 calories. No, that pecan. What do you guys think how many calories a pecan depends on? Would you guys agree? Would it depend on the size of the pecan? So really, what would be more informative if you guys were to do this experiment and try to publish or declare or communicate the information you gained to somebody else, rather than saying, oh, the pecan is 3 calories? Wouldn't it be, what do you think you could do so you could utilize that information so you could compare it? So like, let's say somebody wanted to know, should they eat pecans or almonds if, for example, they're on a diet? So they want to know which is going to be lower in calorie. Could you use your value and then compare it against an almond? No, you couldn't, because what's to say, you know, that you didn't use a small pecan and they're eating a large almond, or they're eating a small pecan and you had a large, whatever. You guys get what I'm saying? Does anyone know? Anyone know? I feel like I'm in the classroom. So I want you guys to be thinking about, what could you do? You know what you would do? You'd say, okay, well, it's 3 calories. Well, how big was my pecan? You guys remember before, I don't know if you guys picked up on it, I said it was about 10 grams. So I'd say it's 3 calories per 10 grams. So what do I come to? If I do my math, basically, hopefully you guys see that this information is value is a lot more informative than just 3 calories. What I'm telling you is, I would say pecans rather, are 0.3 calories per gram. And then I could take that value and then compare it against the calorie per gram for other food items to see which one indeed has a higher caloric content. Okay guys, hopefully you guys followed that. I'll see you guys at the next live session. Bye.